We have a few more examples left in our central limit theorem section. I'd like you to take a moment and try this example 5 on your own. See if you can come up with the graph, the probability statement, and how you would input it into Excel. Pause the video at this point, and when you resume, I'll walk you through the correct way to do it. But I want you to try it on your own. We've talked about how important learning from our mistakes are, and it's really good to, when you're beginning to learn something, to try. So pause, try it on your own, and then when you resume, I'll continue with the problem. Here in example 5, a survey found that the American family generates an average of 17.2 pounds of glass garbage each year with a standard deviation of 2.5 pounds. Find the probability that the mean of a sample of 55 families will be between 17 and 18 pounds. Average of 17.2 pounds, that's my mean. Standard deviation, 2.5 pounds. Sample of 55, that's N. And I want them between 17 and 18 pounds. So that 17 and 18 is going to be my probability statement. On the graph, let's label our mean, 17.2. And we're looking for between 17 and 18 pounds average. So my probability needs to be between 17 and 18. So we'll say 17 less than x less than 18. We're going to make this x bar because we have a sample and not an individual. And before, when we did a between, the problem right above, we had to do two norm.dist functions. Always the higher value minus the lower value. And the other thing that we need to take into consideration is our standard error. We need to make sure that we have our calculation of our standard error somewhere where we can either put it in technology and have technology calculate it, or if it's easily calculated by hand, we could do that too. This one is not. So standard error is standard deviation divided by square root n. So we'll have 2.5 divided by square root of 55. And I'm going to make Excel calculate that for me. So for the probability, norm.dist, 18, our mean, our standard error, and true, minus norm.dist, 17, 17.2, standard error, and true. So working in Excel to find my standard error, 2.5 was my original standard deviation, and I will divide that by the square root of 55. 55 is our value for n. And I hit enter, and I get 0.3371. This could have more decimal places to it. And sure enough, we see that it does. There are a lot more decimal places after that. If we leave it in Excel like this and we don't, we're just moving the decimal place around to see other variables, we can just click on that and use the true value for the standard error. So don't round it in the middle of a calculation. Leave it as it is. And we'll start out with norm.dist, 18 is first. 17.2 is my mean. I'll click on my standard error for the cell reference, and we'll type in true, minus norm.dist, 17, 17.2, click on my standard error, and true. Remember, I want a probability. What is the probability that an average of a sample of 55 families will generate glass garbage between 17 and 18 pounds. And we hit enter, and we get 71.5%. Great. Taking a look at the next problem, the average age of chemical engineers is 37 years with a standard deviation of 4 years. If an engineering firm employs 25 chemical engineers, find the probability that the average age of the group is greater than 38.2 years old. We'll start out and identify our mean, identify our standard deviation, identify our n, and we're looking for the probability of the group greater than 38.2 years old. So let's draw our graph. Our mean in the middle, 37. We're looking for greater than 38.2. So I'll put it somewhere to the right of 37 since it's bigger than 37. Greater than means we're looking to the right of 38.2. Do you remember what you needed to do to find areas to the right of a value? You'll have a moment to think about it. We need to calculate our standard error, sigma over square root n, so 4 over square root 25, which would be 4/5, or if we're putting it as a decimal value, 0.8. This is an exact value. The square root of 25 is a perfect square. Square root of 25 is 5. 4 divided by 5 is 0.8. So now let's calculate our probability. We're looking for the average to be greater than 38.2. And to get greater than values, we need to start out with 1 minus, and then the norm.dist. The value in question, 38.2. Our mean, 37, standard deviation, 0.8, and always true at the end of these norm.dist functions. So we'll put it in here. I need my equal sign, 1 minus norm.dist, 38.2, comma, 37, comma, 0.8, or you could do like we did in the previous one and create another cell to calculate your standard error. You don't have to do it by hand. Do it on your calculator, do it in technology, and then true. Hit enter, and we get 0.0668, 0.067, or if we're wanting a percentage, 6.7%. So 6.7% is the probability that the average age of the group is 38.2 years old. Talking about the next example, this one is directly related to the one before. It's talking about the same engineering firm. So we have the same information. Chemical engineer, average age is 37 years, standard deviation is 4 years. That engineering firm employs 25 chemical engineers with an average age of 38.2 years. Sorry, I left that out. Would it be safe to assume that the engineers in this group are generally much older than average? Well, the probability that we have an average greater than 38.2 was 6.7%. Sorry, I need to modify this. With an average age greater than 38.2 years. I want it to match my problem from above. So the engineering firm is employing 25 chemical engineers whose average age is greater than 38.2 years. We just found that the probability that the average age is greater than 38.2 years is 0.067. Now this is greater than 0.05, so we can say it's not necessarily unlikely. There is a probability that the group is generally much older than average. We could say that because the probability of being greater than 38.2 is pretty small. It's another one of those gray areas in statistics where you have to make a judgment call. We can also look at this situation in terms of percentiles. So percentiles from chapter 3, a percentile for a value tells us what percentage of the population is below that number. This, however, is not a percentile. We would need to switch the inequality to be less than 38.2. But once we get this probability here, that's super easy to calculate. Less than the same value, 1 minus 0.067, which would give us 0.933, meaning 38.2 is the 93rd percentile. 93% of the 25 employee firms have average ages below 38.2 years. Now, 93% is pretty high. It's a pretty big percentile. So we could, in this respect, say that they are generally much older than average because their percentile is so high. Or because the probability that they're actually that old is pretty low compared to our population.